Okay, so speaking of important things, water, absolutely important. I mean, you know, there's a name, another, what do you call it, a moniker, another name for planet Earth that I really kind of like. It's called Oceanus, and it reflects the fact that, come on, we're basically an ocean planet with a bit of land. It's mostly ocean. It's, you know, right, three-quarters ocean. So water is really important, and we've talked about life on other planets and all that sort of stuff, and I've mentioned that, you know, the thing is to find water. If you find water or evidence of water, then that's, you know, that's kind of an alert. That's where you need to be looking for life. And we know that only because of the way life started on Earth. You know, life on Earth began in the water. So we understand that water is an essential you know, chemical compound necessary for living organisms. So if we look on other planets or moons of other planets and we find water, you know, okay, what kind of reasoning is that, by the way? Oceanus, I spelled wrong. Holy cow. What kind of reasoning is, geez, without the J. If I'm going to say, hey, if I look out there on another planet and I detect water, then I can, you know, I can be, you know, have a reasonable hypothesis there's life. Everything on Earth that we've looked at, has needed water to be alive. Therefore, water is what you need to be alive. So if we see water out there in some other planet, what we're doing is we're engaging in deductive reasoning, okay? Here's the confusing part. We used inductive reasoning to make the statement that if there's water, then there's life. But when we looked someplace else and we said, water, maybe there's life, we deduced it, all right? Yeah, that's right, Clarissa. So we used inductive reasoning to be able to make a deductive statement, okay? Look those over. Find those examples online because they're so important because they say a lot about the way we answer questions and use those questions to make assumptions, okay? There's even some, all right, so everything on Earth that we found so far, every living being needs water. Right? It's an essential ingredient. You and I and the plants, bacteria, everything that we call living on Earth needs water. So therefore, we use these you know, independent observations, right? That we say, all right, this thing needs water to live, and this needs water to live, and we make a general statement. So what we're using is inductive reasoning to come up with this inductive statement. So the inductive statement is, I shall proclaim that everything that's alive needs water. Right? You see what I mean? So that's inductive, right, Sadie? So I'm going up. I'm building up. I'm looking at a bunch of little critters, and I'm saying, this is life, this is life, this is life, this is rock, this ain't life. All right? And I'm saying, what do those critters that are alive have in common? Oh, it's water, among other things. They need water. Let me turn my camera on so you can see that I'm trying to... Yeah, okay, good. Now, when we then look out on another planet or a moon and we go, woo, looking through our telescopes and we say, wow, looks like there's water. Now, I don't want to get into how they know that because I'm not a physicist and well beyond what we need to talk about. But they go, there's a good chance this distant planet out there, this exoplanet, has got water on it. Therefore, it's a reasonable hypothesis. You hear, you know, detectives, well, then I deduce that there may be life out there, right? So you deduce, you use deductive reasoning. That's why people get them confused. They think they're separate, but they're just two parts of the same thing. They involve our ability to make a generalization, and they allow our ability to take generalizations and make predictions, right? Everybody got that? It's really important. If you don't keep working with it, like I said, it is kind of a tricky concept, but it will come to you. You know, and the best way to do it is just get online and find example after example after example after example, and just go, okay, I got it. There's even tutorials and drills, all right? Okay, so the thing about water, of course, is here's water molecules, and they interact with one another, right? They have bonds between one another. We mentioned the ionic bonds and the covalent bonds, but this is one of the bonds that I mentioned at the time and will continue to mention is the weakest of all bonds. You can break a hydrogen bond by just tipping a pitcher up and, you know, stop pouring water. But even though it's the weakest, these hydrogen bonds are some of the most important. Now, that's a relative term, but important to us. Important to us, water needing thingamabobs, right? We need water. And so those slight little hydrogen bonds that barely tug on each other because the molecules have that special type of polar covalent bond, they're really important. They keep water together. They allow us to do a bunch of things. When I say us, I'm talking about us living things, right? Because of the physical property of water, and this is one of my favorite parts of talking about this kind of stuff, is when we mix disciplines together. You see, living things are chemical equations, chemical reactions. We're very sophisticated chemical reactions. But like our genetic molecule, hold on one second. Let the dog in the door, maybe he's interested in the lecture too. But anyway, when our genetic molecule came together and we went, and made that code, the adenines and the thymines that we'll talk about later on, you went from the chemical to the biological. But it wasn't like a jump, it was a gradation. We still argue about what's alive and what's not alive, right? But so back to this idea of water, because of its physical properties, which are things that physics was invented at the moment of the Big Bang. Boom, physics, right? Or maybe before, but I don't know. But anyways, it was a long time ago. You jump off a cliff, I don't care if you're a rock or a human being, you got to obey. Living things cannot disobey the laws of physics. You can't jump off of a rock unless you're a bird and not have gravity affect you. Okay, so first, water molecules stick together, huh? Yeah, the cohesion. We just talked about that. And of course, what's important about that is the idea that if you're a tree, you don't have to question why that's important, because you got to get water up the tree against the force of gravity. Gravity still applies to water molecules, right? They're small. If I dropped a water molecule, okay, negating wind and friction and all that sort of stuff, so like in a vacuum, there you go. If I dropped a water molecule or a brick off of a 10-story building in a vacuum, which hits the ground first? The water molecule or the brick? Jessica says water. What else y'all think? Yeah, so you remember gravity. Gravity is a constant. Okay, so that means that the amount of force that's pulling you down onto the Earth, actually into the center of the Earth, is the same amount of force that's pulling on each one of those water molecules. So it's not like you can say, wow, water being so light, it's easier to pull up. Now, they wouldn't fall at the same rate because of wind resistance and friction, but in a vacuum, none of that exists, right? So that law of physics, that what's his face, I don't remember the dude who did it, that's why I didn't give that example. He dropped him off the Leaning Tower Pisa, a big steel ball and I don't know, something else. It's the same amount of force. So water molecules, even with their little tiny bits of adhesion, hydrogen bonds, very, very weak, but sticking together and sticking to the sides of these conducting cells. You can learn more about those in Bio 2 if you want to know their names and all this kind of stuff. But look at them. That's why wood is porous, right? Water goes through it. So these water molecules moving up these cells and with each other are slightly sticking to one another. Remember, it's what causes that U-shaped meniscus in a graduated cylinder. See, it looks like a U, but remember, in the three-dimensional world, it's actually a bowl, right? So same thing that you can watch. It happens much better on glass beakers. And remind me on Lab Tuesday, and I'll show you, or next week, and I'll show you that. We're doing Lab 2, by the way. Lab 2. Remind me to show you the meniscus as a whole complete dome. All right, so water molecules pull against each other. That's great for trees because they need to get water out to the leaves, right? The water falls down on the roots, but it's got to get out to the leaves. This is great for the spider. I was just talking about this in Bio 2 the other day because I think it's so cool. The spider spreads out its legs and walks on the surface of the water, and it stresses those water molecules. See, because remember, they're kind of like springs, I said, those hydrogen bonds. Hydrogen bonds are like springs. They can spring back and forth, and you can overstretch a spring. So, that spider can do that, but of course, we couldn't do that. right? We couldn't do that. All right. The ones I boxed together, I think that's where I stopped last time. The ones I boxed together, I did so because they are two separate physical properties, but they're what they do for living things are very similar. Okay. All right. So we're talking about this stuff called high specific heat. Now, don't get lost in the terminology so much. You need to know the name to associate it, but don't figure out what we mean by specific and all this kind of stuff. There are definitions for that, which you'll be introduced to in physics if you take that. But basically, this is what it says physically, is water's property of high specific heat means that water molecules can absorb a lot of heat before they break. In essence, in general human terms, a watched pot never boils. You ever heard that before? A watched pot, like if you're trying to boil for hot dogs, man, and you're hungry, and you put you put it on the stove, and it's like, jeez, I'm just trying to boil a cup of water. It even takes a long time in a microwave, doesn't it? You would think in a microwave, when I was a kid, microwaves were really strong, super strong. They had to change them because folks with pacemakers were getting messed up. But you put a burger in there, a cold burger, right out of the fridge, 30 seconds, it was piping hot. So, unfortunately, like it's birds and everything were dying around these areas. But the reason why it takes so long to boil the water is because before you see where it says break and release the heat when they form, before you get a chance to break these molecules apart, because that's what turning liquid into steam is, folks. It's all about density. Solids have greater density. The molecules are closer together. Water's weird that way. We'll get to that. Water or liquids have medium density. The molecules are, whatever, and the medium distance away. And steam of whatever has lesser density, and the molecules are further away. Now, the way they're getting further and closer away is they're bouncing on these hydrogen bonds. And as you heat them up, they bounce more, and they bounce more, and they bounce, and they bounce. Can you see my hand? Yeah, there we go. They're bouncing, and they're bouncing. And finally, the pot is getting hot. You can hear all that noise. You're like, oh, my goodness, finally I can eat hot dogs, right? And then eventually, if you're waiting to steam them, okay, eventually those water molecules, bing, those springs break. I should take a rubber band. I'm afraid I snap myself in the fingers. But anyway, the springs break and the molecules go from liquid density, medium, to very less density. And they float. They float up as water vapor. See? Laws of physics, okay, laws of physics. I haven't talked about biology yet, so if you're trying to go, where's the biological part of this? Hold on, I'm not quite there yet. Let's go down to the next one first. So that's why they're boxed. High heat of vaporization. So what that basically says is in a glass of water, you got to break a lot of those springs. You got to pop a lot of those hydrogen bonds to turn it into steam before this thing evaporates, before this liquid evaporates. And evaporate, by definition, remember, is a liquid to gas, right? Liquid to gas, evaporation. That's how water turns into a gas from a liquid. It's 3 states of matter. Is it evaporates, right? So whether you had physics or not, you probably got this in a general science class, right? It makes sense. This high specific heat means that you can heat water a lot up before it changes state, okay? And the high heat of vaporization means you got to break a lot of those bonds for it to change state, for it to evaporate. Okay, let's look at the biology of this, right? Because that's what this is all about. We got the chemistry, but now let's take a look at the biology of this. Let me, where am I? Right here. We're going past this, and we're going right. Yeah, there we go. All right, so what I've done is I went in and I've kind of summarized. This is in your book, and maybe, I don't remember how much of it I changed. It depends. But anyway, here's the summary of what this all means as we kind of make our way to understanding biologically. Water absorbs heat from warmer air, and it releases stored heat to cooler air. All right, so that's a moderation of temperature. So what that basically means is where we live in Florida, believe it or not, being surrounded on 3 sides by water, it's actually cooler. I was going to say a lot cooler. It's not that. It's actually cooler than it would be. Think about what you've heard about in the middle of like tropical rainforests. It's hot, man. I mean, it's like Tarzan hot, huh? Okay, so water absorbs heat all the oceans from the warmer air. And then at night, when the atmosphere begins to cool off, then the air is cooler. And so at night, the oceans around us give us those nice siesta-key sunsets. Yeah, the water, the heat is being slowly released from the ocean into the air, and it's a nice warm breeze. Now, contrast that if you've ever been to San Diego. San Diego gets hot now. San Diego's very dry. There's not as much moisture, so there's not much water. It'll be a nice, comfortable, yes, 85 during the day, right? It'll be 85 during San Diego during the day, and at night, it'll drop down that you need a jacket. It's that cold. Doesn't happen that here, does it? Our oceans around us act like the same thing or in the same function as the radiator in your car. And if you've ever overheated your car, you know what the steam was coming out of was that thing in the front called the radiator. Works the same exact way. The oceans on Earth, thank goodness, 3/4 of them, for our benefit, us critters, us living things, keeps it, within livable range. We're not doing something like on, let me go up a couple of slides. On Mars, there's the temperature extremes on Mars. So if you were watching Tom Terry on Mars, this is your low tonight. Those are averages, obviously. And then your balmy high of 32 degrees freezing. Now, there might be organisms that survive. There are organisms that live in those kind of conditions, but like Elton John says in Rocket Man, it's no place to raise kids. It's cold, man. Minus 103 degrees. The coldest I've ever been in was minus 70 degrees Fahrenheit when I was in Chicago, and that was miserable. All right, those of us used to living in Florida or growing up in Florida, we would die first night, no matter how much clothes I had on. But it's it's the water that allows our Earth not to do that. Now, yes, I know Mars is a little bit further away and blah, 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 and all that stuff. But the temperature change is much more even given the distance, right? The temperature differences in the temperature change on Mars versus on Earth, right? So the oceans or water can absorb a lot of heat, and they don't change temperature much. All right, here's the problem. When water changes temperature, actually when it changes state, the energy from all of that is released, okay? So keep that in mind. So when water boils, the energy, the heat is energy that was warming it up is released. It's released when it turns into steam. Okay, so let me type that into the chat box so I can remember to go back and emphasize that. Release energy as steam, okay? That's what's going on. All right, so just keep that on the bookshelf for a second. Water has high specific heat, all right, the amount of water, blah, blah, blah. I'm not going to ask you these numbers. If I do in the exam, punch me or something. If I do, then I'll tell you the answers. But anyway, these are definitions of calorie, of what we call a calorie. And a calorie is energy, folks. That's what they're trying to tell you here. It's the amount of heat it takes to raise 1 gram of water 1 degree Celsius. You're like, why 1 gram of water 1 degree Celsius? Standard. That's all. They're standardizing it. They could have said 10. But if they'd said 5.7 grams by 8.3 degrees, you're like, oh, what a pain in the butt to do all the calculations for that. It's all very straight 1-to-1 here, right? Okay, so water has the specific heat that what it says is it takes 1 calorie, and what we call calories in food, by the way, low calories. We just shorten the word because it sounds better than saying you ate, what's a Big Mac, 800 calories? It's actually 800,000 calories, right? So a calorie is the amount of heat to raise the temperature, 1 gram of water, one blah, 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 blah. If you were a physicist or a chemist, you might go, wow, that's a lot, right? That's a lot, that value. I know you're looking at it now, and honestly, I'm looking at it, okay, whatever. But down below, I summarize it, and I say, that value, if you were a physicist, would say, wow, water resists changing state. It resists changing temperature, state. It resists boiling. It takes a long time to boil. It resists changing into steam. Why? Because when it changes into steam, it releases energy. Now, I haven't finished that part of the vignette, right? I'm still emphasizing the idea that when water's boiling into steam, it's releasing energy. I'm getting ready to make this bridge into the biological here. Okay, so right, we got this whole idea of these things bouncing, 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 and the fact that they can bounce means that your body doesn't go through dramatic temperature fluctuations. All right, normal body temp for human being, folks. Celsius, not Fahrenheit. If you know the Celsius, what's normal body temp? I'll tell you room temp is somewhere around 20 to 25. You take A&P, you'll learn this if you don't know it already. No guesses? Close, Marie. Close. Patrick, remember that's Fahrenheit, and Fahrenheit is an acceptable temperature means, but we don't use it in science. We all talk in the same language. There you go, Aura. 37 degrees. 37 degrees. It's actually easier than 98.6, right? So when your body temperature moves off of that enough, and you can learn about that all in A&P if you take it about how far it goes. But you're unbalancing, right? You're unhomeostasizing. You're getting that teeter-totter screwed up. So when your body moves away from those critical standards there, that's a lack of homeostasis. That's a problem. You're gonna get overheated from that. You're gonna get sick. Any kind of homeostasis. So the springs kind of help you maintain homeostasis with a little flexibility. Now, again, something we don't know a whole lot about, but I remember out in California, everybody talking about how the buildings were built on like slip pads, like this huge skyscraper. I ain't no engineer, so sorry for this. But here's the foundation. It wasn't like exactly attached firmly. It was, but it was attached in such a way it could move back and forth. Now, do I need to explain to you why that's good for buildings in California? Someone tell me. There you go. Perfect. So it's a little bit of fudge. It's a lot better than attaching it firmly and the doggone earthquake comes and knocks it down, right? So homeostasis in the city, homeostasis in your body is flexibility. So those hydrogen bonds are not only easy to break and do important things like hold water together, but they hold water gently. They hold it with a spring so that your water molecules in your body can absorb the heat before they turn to steam. Okay, let me ask you a question. If your water in your body turned to steam, what happens to you? Nobody want to try it out? Now, yeah, you die. Heck yeah, you die. You die fast, right? That's one of the quickest ways to die. Here's what's happening. Now we go back to released energy is steam. Now here it is. If that happens, all the energy was being absorbed by these springs on the water molecules. The springs break. I'm going to knock my water over. The springs break because you go from liquid to gas. Okay, this and when the springs break, all that energy was being absorbed. All the things that was all the energy that was making those springs go it gets released into you, right? As destructive energy, heat energy. It starts destroying enzymes and cells, blah, blah, and you die, okay? So water, oh man, isn't this cool? Water with those slight hydrogen bonds does things like allow us to live in temperatures in a planet that aren't so extreme like Mars, and it allows you to enjoy these, look at the temperatures there. Palm Springs is 106, this is one day, on one day. Wow, San Diego, oh my gosh, 72. Man, if you've never been to San Diego, I was stationed out there. It's beautiful. I went out there a couple of years ago for a business trip after I've been stationed out there in the Navy, and I rented a convertible because I just had to, right? I'm just fried the top of my head. But, oh, look at the temperature in one day. I remember specifically when my ship was stationed up near Los Angeles in Long Beach, that the opposite. In the wintertime, as a bunch of us Navy guys could drive up into the mountains near San Bernardino, I remember, go skiing, right? This was like March, and go skiing. And then the next day, we could drive down and actually go to the beaches. And that's all because of what's happening out there in the ocean. See, the ocean is a little further inland, Palm Springs, San Bernardino, all that is near the desert where it's dry. Near LA and San Diego, Santa Barbara, right? Water, so it's cooler. So when you're sweating your tail off here in Florida in the middle of summer, just say, thank goodness we're surrounded on three sides, because if we weren't by water, it'd be a lot worse. Now, of course, the humidity doesn't help. But But man, Palm Springs at 106 is hot. I don't care what. Okay, so it does really good for us when it comes to living collectively on the planet, right? Why? Because water absorbs that destructive energy. Doesn't absolve you. Like I said, you can boil, of course. Now, when it comes to an individual organism, so think about what I've been talking about is good for us on Earth. As an individual organism, sticking with that homeostasis theme, because water does that, because it takes a lot of energy when water turns from a liquid state to a gas state, okay, it also can be used. Now, as I said, boiling is the same thing, but you're releasing an energy all at once, right? You're boiling. Now, if you don't boil, if you simply sweat, if you simply perspire, like this dude in the green jacket here, it looks like, when I first moved to Florida, the guy I worked for a burglar alarm company, and back then they weren't wireless, so he ran wires, and he looks at me, and they're in the interview, probably completely against HR, says, how much do you weigh? At the time I weighed like $115, and he said, oh good, you'll be perfect. So what they did is made me crawl around attics. I moved to Florida in August, so it was really nice up there. So anyway, I was very happy that what was happening is I was sweating a lot, because what was happening during sweating goes back to, hold on, don't lose me for a second, right here, heat of vaporization, right there, high heat of vaporization, which again, many hydrogen bonds must be broken for water to evaporate. So when water starts evaporating, it breaks a lot of hydrogen bonds. When water starts boiling, it does too, but that's not good. You want it in little bits. So the water boils, turns to a gas when you sweat. And because it takes a lot of energy for that to happen, you lose a lot of that heat when that happens. So the amount of heat that 1 gram liquid must absorb to be converted to gas. You see what that's saying? Don't worry, you can put the 1 gram again. But what that's saying is when that happens, when you sweat, you're releasing a lot of energy. You're cooling your body off, right? It's called heat transfer. That doesn't work as well in Florida as it does in other parts of the world or the country because we're so humid. And if you think about it, the air has already got a lot of water in it, and water that old adage of water flows downhill, if you will. Water goes from where it's watery, more water to less when it comes to evaporation. And unfortunately, there's, things don't evaporate here in Florida. That's why you have to be careful of heat stroke. If you're outside and you've been working and you're hot and you're not sweating, you need to go inside. That means your body is shutting down. So animals out in the desert, like is this the Thompsons? I think this is a Thompson's gazelle. Use this to their advantage in a really kind of cool way. And I found a neat picture online. If you look, this is a skull, obviously, of the Thompson. And one of the things that you want to keep cool, obviously, is your brain. Your brain gets hot, and things really start getting screwed up. So what they do here, these organisms, through evolution, they rerouted their bloodstream so that the carotid artery. Now, the artery is what brings it from the blood, from the heart. Veins bring blood back to the heart, and arteries take blood from the heart to the rest of the body. So this blood has been circulating from the heart. It's not a far distance, but it has been circulating through this hot Thompson gazelle. So it's kind of warm. So you notice it doesn't really exactly go completely to the brain. It seems to sort of circumvent it. This thing is a net of blood vessels, a very fine net of capillaries, and heat can be transferred. But before that warm blood brain, one more time, before that warm heart blood goes by the brain or supplies the brain, it first goes to the nose, where when the animal inhales cooler air, relatively speaking, still doggone hot in Africa, the cooler air, like the radiator of your car, cools off the blood, and then it goes back to the brain when it's been cooled off. Not only does it cool off the brain, it also helps remove some of the heat from the brain. So it works very much like the radiator of your car. Isn't that neat? And all of this occurs because of that special little net right there that I circled. That thing right there. Okay, so are you convinced enough about the idea that water's high heat of vaporization or water's high specific heat or any of that stuff that we've been talking about, how important that is for living organisms? Right? Any question of that? we wouldn't survive. We just would not survive because the temperatures would bother us. You know, we would walk out of our class of a warm 25 degrees out of the hot parking lot in August, you know, where it would be, you know, maybe 45 degrees Celsius, much warmer. And that kind of shock your body couldn't take. But the springs in those water molecules help you deal with that. Any questions on that? All right, so I bring the arrow down. To sum up what I've been trying to say all along, water moderates your temperature and the world's temperature and anything's temperature. Water evaporating off of a concrete surface is removing heat from that surface. Okay, let's see. Oh, good. No, let me go back one. Ice. Let's talk about ice for a minute. There it is right there. All right, let me jump ahead because I'm going to show you a picture. This is one of those things where I'm trying to see if I can get you to do an ooh-ah kind of thing. Not that it's that ooh-ah. You know, ooh-ah is like, wow, oh, that's kind of cool. It's just interesting, especially when you look at the way it works. Because, you know, as kids, we like to take things apart and see the way they work. Some of us do. And even if you're not, if you're artistic inclined, you'd like to be able to create things. So it's the same kind of idea. Here we go. Put solid water into liquid water and it floats, right? Ice. Okay. Is ice a solid? Give me a yes, no, emoji, something like that. Not a trick question. Is ice a solid? Yeah. Would you rather me throw an ice cube worth of water at you or an ice cube at you? Ice is a solid. And liquid water, or iced tea, which is made up of mostly liquid water, is a liquid, right? So we got a solid, which I just told you means it's greater density, floating in a liquid, which is of less density. And nobody ever questions that. You don't think about that when you drop ice into your glass, do you? Like, hey, wait a minute here. I never noticed that what's going on here is a solid is floating in a liquid. That can't happen because here's benzene on the right. Benzene is a material, I don't know its chemical compound, doesn't matter. But it's very similar to water, relatively similar to water. And when you put frozen benzene and liquid benzene, right to the bottom, because if I put a rock into water, doesn't it sink? All right, why do things sink in other things? What is the physical property, or what is the property of an object that determines whether it's going to sink in something or not? Now, if you're going, what is he talking about? Lab 1. Very into Lab 1. Why wood floats and rocks sink. Yeah, thank you. Thank you. Yes, exactly. So the benzene here that's solid must be more dense than the liquid benzene, correct? Yes. Yeah, thank you. I'm sorry, if the lag is doing it, I'm not trying to be rude. I'm just making sure that it... Okay, now, we don't question it in ice. Now, that's a physical thing. Let me show you first why that happens. Why the laws of physics seem to be defied. They're really not defied. Water has its maximum density. In other words, you're cooling water off, and the molecules are getting closer and closer together at about 4 degrees Celsius. I don't know how to make a degree symbol here, so anyway. At about 4 degrees Celsius. Now, you may not be completely familiar with the Celsius system, but we all know probably 0 Celsius is freezing, right? It's 32 in Fahrenheit. It's 0 in the Celsius system. So what we're saying is density, which is what we think of now as solid, liquid and gas. The density of water is its greatest when it's still a liquid. Yeah, 4 degrees is still a liquid. My wife will always say, do we need to cover the plants tonight? It's going to get down to 37. I said, well, they're not going to freeze. She said, well, why not? I said, it only freezes if it doesn't. She goes, there's not a range? I'm like, no, it freezes at 32. We don't have to cover the plants even if it's 33. Okay, so at 0, the water freezes. Now, why would something that's still a liquid, but very cold, I wouldn't want to be swimming around in 4 degree Celsius water, why would that still, why would that liquid still have a greater density? All right, it's all about the hydrogen molecules. One more time, folks. Here's another picture. See all the hydrogen bonds, the yellow dashed lines? Okay, there's liquid water, right? Now, liquid water is springy. We know that. They spring. As you would heat up this sample of water, those springs would springier. They would more spring, get further apart. Eventually, when you get them too far apart, right? They turn to steam. Now, we're going the other way. We're cooling them off. So now what happens is the springs are compressing. Well, this is where my spring analogy falls apart, because when water molecules get really close to each other, about 4.5 angstroms. We didn't even do angstroms in the metric because an angstrom, see, if I remember right, the smallest one we did was nanometers. I think it's 1,000 angstroms to a nanometer, if I remember correctly. Now, don't quote me on that, but it ain't very big. I wish I could give you one of those the size of a human hair, but it's pretty small. All right, now, when water molecules get that close to one another, the springs, they don't act like springs anymore. They start to act like girders, you know, stiff structures, and they actually begin to push the water molecules. Okay, hello, hello. Hello, I'm back. Can you hear me now? Okay, I'm sorry. I noticed that the other day in my bio too, it does that every once in a while. It cuts out. Just it takes me a second to come back. Just type it in and let me know right away when it happens. All right. So I'm not sure where I stopped, but you couldn't. Yeah, it's something. The signal gets messed up. Thanks, Isabel. So I think where I stopped was I saying that water at 4 degrees, even though it's a liquid, the hydrogen bonds are a little further away than they are when it's frozen. See, this is solid ice, right? So that's solid. The hydrogen bonds become rigid, so they go from springs somehow convert into girders, you know, a stiffer structure. And because they moved out just a little bit, because at 4 degrees they might have been, they might have been something like 3.8 angstroms. So they'd be a little closer together. Because they froze, and because of the physical properties of water, they push out just a little bit. They push out to 4.4 angstroms. So they decrease the density after you cool water off at 4 degrees. Now, that's not something that happens in all substances. That's unique to water. That's because of those hydrogen bonds, okay? Those hydrogen bonds allow that to happen. Physics, biology. All right. If I were this little shrimp, I would like the fact that when the water freezes in a lake or in the ocean near the coast, it freezes at the top. And it only does that because it's less dense. I just showed you that in the iced tea. For one thing, the little shrimp can feed on stuff that attaches itself to the bottom of the ice, but really the big problem would be that if a lake or waterways near the ocean froze solid, or if ice sank, when the water froze, it would fall to the bottom, and eventually the ice would, or the lake would freeze solid. That would kill, if it were in the ocean, that anemone, and this husky would have a really hard time walking across that lake. See, because ice floats, during the wintertime, organisms that live in those cold water ecosystems can still survive, because even though it's ice on top and the dog can walk on it and you can skate on it, it stays liquid down below. And these organisms, an invertebrate, or especially not a mammal, if it's cold, it doesn't really bother you that much. As long as you don't freeze, you're okay. And since the air might get minus 10 degrees Celsius, right, and it can, the water is never going to get any colder than just a little above freezing. So it's going to be the difference between life or death. Orange growers do the same thing. What do orange growing folks do when they know there's a freeze coming to their crop? You guys live in the middle of some of the biggest orange groves in the state, so I would expect you to know this. I'm sure some of you know orange growers. Worked for orange growers, right? They're all over the place. Drive down 441 before you get to Mount Dora. Nobody knows why they take the water? Yeah, they cover the plants with ice. And when you cover the plants with ice, with that same thing as that anemone in that picture growing underneath the coastal water there, even though it's frozen at top, it's liquid down below. So even though the ice on the plants may affect the cells of the plants, and maybe some of them will be damaged. It's frozen, okay? But if the plant has the ability to deal with that, that's good. But if the outside air gets to 30 degrees or 28 degrees, or God forbid, sometimes I remember, well, a couple times, it would get down in the upper 20s, then those 2 or 3 degrees are the difference between life and death, right? So thank goodness ice floats, huh? We can water ski. Yeah, we can water ski on ice. We can skate. The husky can safely make it across, and other critters can live their life, and the bass will be alive next year when we want to fish for them. Now, we don't worry about any of that in Florida because thank goodness our lakes don't do that. Now, the last one I want to talk about is something known as solubility. First of all, let's do a little definition thing here. Solubility is when we take a solute. Now, solute is that which is getting dissolved. In my picture on the right, we're dissolving salt, sodium chloride. So in this case, the solute would be the salt. The solvent is that which does the dissolving. So if we're dissolving sodium chloride in water, that would be the water. And then together they make a solution, right? Solute, solid, solvent, liquid. A solute could be a liquid too. You can dissolve one liquid in another. But one does the dissolving, one gets dissolved. Typically, you think about it as a solute. The word aqueous, if you see it, you might see it on prescriptions sometime. What they're telling you when the word is aqueous, a fancy word of saying the solvent for this material, this prescription, is water. Okay? Now, the fact that we say water is soluble, okay, we understand that. You put sugar into water, you put salt into water, and it dissolves things. But when we start talking about cells here in the next few chapters, we're going to talk about the parts of the cell, or these things that we call the organelles, and we're also going to talk about the cytoplasm. The cytoplasm is the, I'm going to say at the time, the liquid portion of the cell, the things that the organelles float in. You've all seen pictures of cells, you know what I'm talking about. Most of that cytoplasm is water. It's unique to me, or interesting to me, that the Earth is, 2/3, 3/4 water, and so are human beings. So we're about the same. Well, so are living things in general, right? So that water that's in the cytoplasm is a solvent, right? It is that which is doing the dissolving. So it dissolves lots of things. And as I said earlier, living things are just a chemical reaction. So the fact that you have all these things in a chemical reaction in this soluble substance, this thing which dissolves everything, it means there's a lot of mixing going on. That's what we mean by that. Water is a universal solvent. It's a good mixer. It mixes things. So in your cells, just like it does to the salt crystals in that beaker, it separates things and pulls them apart, and it makes a nice homogeneous mixture. Folks, it's the same reason you put water in a cake and then stick it in the oven and bake it at whatever you bake it at above boiling, right? You bake cakes higher than 212 degrees Fahrenheit, and you boil the water back out. Now, I know not all of it does, but the reason why you put the water in the beginning was to make a nice homogeneous mixture, weren't you? Dough, right? See how that all fits? Now, I mentioned to you in class a couple of weeks ago or so that when eating heavy carbohydrate foods like noodles, oftentimes you would find in Chinese cuisine, can sometimes make you feel full, and then soon after the meal we say, I'm hungry again. Well, that's because ions, which are one of the things, well, among other things in the food, of course, is Chinese cuisine tends to have a lot of salt in it too sometimes, in the foods as well as like soy sauce. But those ions of the salt crystals actually will form these things called hydration shells. A hydration shell is, like I said, if you dropped a lollipop at the beach, the water molecules would be sand. Okay, so that's what happens, is the positive and negative end of the water molecules, right? They're like magnets. Well, they go in, there's negative there and positive there. They go in and start pulling off. And see the picture up here? The negative end of the water molecules are around the sodium, and then the positive ends are around the chlorine. So they form these shells. Now, when you eat salty food, what happens is soon those shells are gone. Your body processes it, and you're not as full as you thought you were, because you're not taking up this much space in your stomach. You're taking up a much smaller space, right? Okay. So water is soluble. This also happens to proteins. Water molecules can move in on these large purple things called proteins. They have positive and negative. Anything, folks, anything that has positive and negative charged parts of it, hydrogen bonds, water molecules can go in and rip apart. So that's what we mean by universal solvent. Now, I don't know if that's universal, some of the man-made stuff, but the things that living organisms usually deal with. All right. Let me look at the schedule here. We're doing well with chapter 3. I don't think I was supposed to start 4 today, but even if I was, it doesn't matter. We'll catch up. So I don't want to rush through stuff. All right, let's talk a little bit more about water and its enemies, if you will, or things that don't like water. So let's discuss what it means to be hydrophilic and hydro. Although you probably know, right? What's hydro? Speaking of that, where's my water? And phobic or philic? How about phobic first? And then philic? There you go, Marie. Philic, what do you think? We all learned in school that Philadelphia was the city of... There you go. Right? Hydrophilic is water-loving. Hydrophobic is you're afraid of water. Now, you yourself could be hydrophobic. Maybe you don't like going out on boats, but we're talking here obviously about substances. So let's look at the hydrophobic ones on the left. Right? These are oils, waxes, fats. Oh, I see the stuff that when I put in the water doesn't dissolve. That's exactly right. Things that are hydrophobic have no affinity. They don't like water. They're repelled by water. That's why, like if you put vegetable oil into water, it'll settle up to the top eventually, but when you first mix it up, you notice like little bubbles of oil. That's because the water molecules are just surrounding the bubbles or the oil. They're not tearing it apart. They're not doing what we saw in the salt crystal. And that's why eventually, because oil is less dense, floats to the top, right? Things that are hydrophilic, well, they love water. They have an affinity. That's what we mean. Now, affinity means in chemistry, it means that you're chemically attracted to. See, oils and water, waxes and fats, they don't mix because there's no chemical attraction. There's none or very little of this going on. I say very little because it varies depending sometimes on certain what we traditionally call hydrophobic substances. Okay, hydrophilic would be things like acids, bases. We haven't talked about acids and bases yet. We will in actually a couple of slides, but vinegar is an acid, hydrochloric is an acid, bleach is a base, sodium hydroxide is a base, and if those words sound familiar to you, that means you remember from chemistry, right? Ammonia, that's a base, sulfur dioxide, hydrogen sulfide, that stinky egg gas that you might smell in swamps sometimes, that's hydrogen sulfide. It comes out of volcanoes. Those things are hydrophilic, so if you mix them together, they will mix, all right? That's because they're both charged. So it's like mixing a bunch of magnets together. They're going to mix up really nice, aren't they? So I use the example of white vinegar. If you put white vinegar, and I say, or clear, I'm sorry, if you put clear vinegar into a beaker of water and stirred it up, they wouldn't separate. The only reason I say clear is because if you put cedar vinegar, then it'll darken the water. But anyway, you understand what I mean, right? You wouldn't be able to tell the difference between. When you get these little acid bottles in lab that when we do labs in the future, the acid is not the liquid. The acid is what was dissolved in the water. Acids are hydrophilic, or if you get a bottle full of sodium hydroxide, same thing. Now, there are some molecules out there that lead a dual life. Okay, there are molecules out there that, because molecules are a structure, yeah, they have parts to them, that they have parts of them that are hydrophilic and parts that are hydrophobic. So the term we use to refer to them is we say both love, amphiphiles. There's other words for us, ambivalent, amphipathic, but amphiphile is the one I like because hydrophobic, hydrophilic, amphiphilic, or amphiphile. These molecules have an affinity for both. So what we mean by that is they're attracted to oils, the hydrophobic substances, but they're also attracted to hydrophilic substances. Now, we'll talk about one of those a lot this semester, but I'm not going to introduce it not until we get to, I think it's chapter 5. But this molecule here is the one I'm talking about. Now, they've simplified that molecule. It doesn't look like a spaceship there, but this thing is called a phospholipid. Now, getting ahead of myself a little bit, phosphate is hydrophilic. Get rid of my scribbling. So it likes water, so it's not afraid of it. And the lipid that I just wrote in there, lipids are another name for fats. They're hydrophobic. So what we're saying, there's a part of the molecule that's hydrophilic and a part that's hydrophobic. Now, I'll talk more a little later on about the specifics or why that's so important for living things, but it's not so weird because that's how your laundry detergent works too, folks. Your laundry detergent, most of the dirt on your clothes is oils, right? Oils, I would say waxes, fats, I don't know, but it's oily kind of stuff. Dirt is got a lot of organic oilies in it. Oilies. So if you put a substance in there that was hydrophilic, it would never get the oil off. But if you put a substance in your washer that was hydrophobic, it would never mix with the water that you put in there that later is drained away with the dirt. So there's a molecule, and of course this was created in a lab, like Tide, for example, and any of those detergents, that are made similar to that phospholipid thing I just told you about. It's got a hydrophilic part, so when the water is drained out of your washer, it goes with it. And of course, it's physically attached to the hydrophobic part. And again, your laundry detergent doesn't look like this, but the hydrophobic part is attached to the dirt on your clothes. Now, if you're saying, well, what about the hydrophilic stains on your clothes? Who cares? Water takes care of that. Water will dissolve that. Unless your hydrophilic, whatever's on your clothes is some weird stuff. All right, moles. I don't really talk a lot about moles. Matter of fact, this is probably one of the only times I will discuss it with you more than just in passing mention. It is something that's important that you understand, but it's not the little burrowing critter that you see in the picture. When we're talking about moles here, we're talking about a way of measuring things in chemistry. So it's similar to like a liter, meter, all those things we talked about in lab. It's similar to atomic mass, or what we call Daltons. So first of all, let me tell you what a mole is and show you how we calculate a mole, and then tell you how we use it. The most important thing I want you to get is what a mole is, all right? And not what it equals. All right, let me start. A mole, which is abbreviated sometimes MOL, has an actual value to it. A guy named Avogadro came up, and I have no idea how he did this, but he says that a mole of anything, a mole of moles, a mole of you, a mole of dirt, a mole of air, has this many molecules in it, some big, big, big number, right? 6.02 times 10 to the 23, that moves the decimal point there, 23 places to the right. That's a number I'm sure doesn't have a name. So that's why we use scientific notation. Now, a molecular mass ties into a mole. A molecular mass is not hard. It's exactly what it says. It says that you take something like glucose, okay, glucose is an example, and you determine what the atomic masses are of each of the element in glucose. So I've done that for you here. Where would you get that? You would go to a periodic chart. That would be the number in the upper left. Now, in chemistry class, that number's not going to be a whole number, but it doesn't matter. You would use the whole number. You multiply that mass by how many there are. In glucose, there are 6 carbons, 12 hydrogens, and 6 oxygens. It's just like we did in class with the surface area for the block, right? Calculate that all up, you get 180. Now, that's just for glucose. If we were doing carbon dioxide, you would add up the atomic masses of carbon and 2 oxygens, and so on. Now, what that tells us, if you went to the cabinet and the doctor or the lab you worked in, or you needed it, you went up and you said, I need 1 mole of glucose. What you would do is you would go to the cabinet, and out of the bottle you would take 100, you weigh it out on a scale, 180 grams of glucose. That's because of Avogadro's number, 180 grams of glucose is exactly Avogadro's number. I have no idea why. Okay, I mean, I know I learned it, but don't worry about that here. So it's just a measurement of a unit of measurement. If you're working in a hospital and the doctor said, I need a mole of carbon dioxide, he wouldn't. You would say, okay, carbon is 12, oxygen each are 16. He wants 2 of those. Now, you wouldn't do this, right? Of course not. You probably wouldn't, I'm sorry. Wouldn't tell you a mole. I mean, but that's what it is. It's a unit of measurement. Again, how 180 grams of glucose and whatever this adds up to for carbon dioxide is that many molecules, you'll learn that sometime and probably forget it if you don't use it like me. So that's 1 mole of glucose. Now, if we take 180 grams of glucose and we put it in 1 liter of water, this is what we have. We have not 1 mole of a substance, but we have 1 molar solution. That's what we call molarity. That's big M. Big M is molarity, little mol is mole. So if someone said, I need a 1 molar solution of glucose, you would take 180 grams of glucose, put it in a liter of water, mix it up, and go, here. Okay? Not hard, right? So if I need a mole of substance, of something, it's how many atomic, it's in grams, the atomic mass of the elements in that substance. Piece of cake, right? Any questions? I am here. Hello? Okay. Good, let's try it. Do water. How many grams is 1 mole of water? Got a couple answers. Anybody else? It's going to be 2 hydrogens and an oxygen, folks. So Jasmine's correct, right? Or is Isabel correct? Which one is it? 18, right? It's 18. 2 oxygens, or an oxygen is 16, 2 hydrogens are each 1, right? Piece of cake. No more about moles. Again, I may use the word in passing. I may, on an exam, want you to calculate the moles of something very, very simple. But as far as you knowing, as long as you know that what we're talking about is a measurement in chemistry, a concentration measurement, then you're good with moles. And you can worry about those again when you do take chemistry. Now, speaking of acids and bases, let's talk about acids and bases for a second. First of all, let's talk about this thing that water molecules are doing. Not very many of them, but in a beaker of water, in a liter of water, in a bucket of water, a very small part of them are doing this thing called dissociation. Now, if that word looks weird, it's just the opposite of association, which means to come together, right? I guess I should write the whole word before I write ASS on the screen. So association is come together, so dissociation is not go apart. Here's what I mean by this. Because you've got those water molecules floating in a beaker of water, and because they're all sticky, right? They all have those hydrogen bonds that attract each other. Then you do sometimes get situations that where you get is an oxygen end of one molecule is one on the left, and the hydrogen end of the one on the right. The oxygen, because it loves protons so much, and I'm trying to think of a good analogy, but I can't really. Every once in a while, that water molecule on the left will actually be able to pull the proton off. It leaves the electron behind. It leaves the electron behind. That's why, because that thing on the left, this hydronium ion, actually has the H3, 3 hydrogens, but there's a plus. That means there's an extra proton, remember? And on the right, this means there's an extra electron. The one was left behind. So very few water molecules are doing this. Just 1 in a few billion are doing this. And for every one that falls apart, since these arrows point both ways, a pair of hydronium ions and hydroxide ions reassociate or associate. So the equation goes back and forth, right? That's what happens in a thing of water. That's what happens with water. Now, acids do the same thing, okay? But I'm gonna show you something down below. Right in the slide, so that we make it a little bit easier when we talk about acids. What is going on up here at the top is really what's going on. What's going on down here is a little simpler way to write it. You notice instead of writing a hydronium ion, I'm actually just referring to the hydrogen ion that got ripped off, and then where it got ripped off of. So the only thing I haven't done is stick the hydrogen ion to the water molecule on the left. That's really what happens. But what you see written down below is just an easier way to represent it when I talk about acids and bases, right? Okay, so if everybody understands that, then the next slide should help us out. An acid, anything that when you dissolve it, dissolves or dissociates into a hydrogen ion and something else. Sometimes we say acids have the general, there's no element X, by the way. A hydrogen ion. I say that's an ion because it's charged. Remember, that's what charged atoms are. They're ions. And in a negatively charged ion, so a cation and an anion, anything that does that, like hydrochloric, sulfuric, is called an acid. See, acids are hydrogen ion donators. Hydrogen ion donators, or donors. Now, hydrogen ions can also be referred to as protons, so aka protons. Think about it for a second. Where's my fingers on the right keys? Spelling something in Old Greek there. Hydrogen ions are also protons. The reason being is hydrogen has the atomic number 1, 1 proton, 1 electron. The electron's gone. It's over here with the chlorine and hydrochloric with the X in my general formula. So all that's left is a proton. These words I'll use interchangeably. Hydrogen ion or protons. Okay, bases are substances that absorb protons, that take up. So they're proton absorbers. Like, for example, sodium hydroxide. Sodium hydroxide, when you put it in water, dissociates. All right? It makes sodium ion. So again, the general formula for bases is something positive, and the hydroxide ion, something negative. Now, what's different between acids and bases on this chart, though, or on this table, or on this screen, is the fact that the equation down below is not quite finished, because what happens with a base is we say that this ion here then combines with a proton in the water. We'll go back one second. Because there are protons in water, because water is doing this, right? So those few water molecules that are breaking apart into protons, what a base will do is it will grab those protons, and when you put those two things together, you get water. So that's why something like sodium hydroxide or potassium, atomic symbol K, is a proton absorber, because when it dissociates, it gives you that negatively charged ion, which completes this equation. Now, bases can be of two types, though. There can also be a base that doesn't need the hydroxide ion, that it itself, like ammonia right here, ammonia can absorb a base, that is, take a base from the water that it's dissolved in and make what we call an ammonium. Okay, I'm back. Hello. Okay, sorry again. So I was saying that another form of base is the one down below, which is ammonia, excuse me. And when it absorbs a base or goes to the right, it forms an ammonium ion. See, because it's charged. So bases absorb protons two ways, and acids donate protons, and they do it basically the same way. And again, what I mean by donating and absorbing, I'm saying that acids, if you dissolved them in water, would give you lots of these, and a base, if you dissolved it in water, would give you few of those. So acids would increase the protons in the water that it's being dissolved in, and bases would decrease the protons. Now, does that make sense? So think about up above. If I take the hydrochloric and I put it in water, water is already, forming these things. So I'm adding to that. On the other hand, with a base, I would be removing from that. All right? Does that make sense to everybody? Because understanding pH is crucial that you understand that. Because understanding the next slide I'm going to go over, we're doing perfect. The next slide I'm going to go over, it's imperative that you understand that. So if anybody has any questions, please. All right, then let me ask you a question. Would you expect an acid X, that when I dissolve it in water, that when it gives up lots of protons would be a stronger acid or a weaker acid? So we can count the protons. So what I'm saying is an acid that gave up tons of protons versus just a few. Which one would be the stronger acid? Think about it for a second. Okay, why are you guys saying weaker or just a few? I'm curious because I'm misleading you somehow. Don't think of it as the type of proton. Think of it as how many. Right? We can count these. So I'm saying acid A, acid B, when I put it in water, gives me tons of those protons, and acid A gives me few of those. Which one's the stronger acid? Which one is more acid-like? Yeah, the one is the better proton donator, right? And what we mean by better is more. Does that make sense? The strength of an acid, okay, I'm going to type this in here. Strength of acid is equal, to number of protons donated. You sabe? Everybody get that? Sorry. Sweet. So now, follow me on this. Strength of a base is equal to number of protons. What? Fill in the blank. The strength of a base is equal to the number of protons what? Sweet. Beautiful. All right, now we're ready. Here's the pH scale. pH actually stands for, it has to do with the logarithm of it. And again, I'm going to show you an easy way. I'm going to show you the math, and I'm going to show you an easy way to look at it. But the reason why the P is small and the H is big is because what we're talking about is we're using a power scale, a logarithmic scale. And that's what you see in the red there. So let's go there first. Whenever we put something in brackets in chemistry, we mean concentration of, wrong brackets. No, that's right, these brackets. So what you see up there is concentration of protons, number of protons, same thing we've been talking about. To get a number for pH, what you do is you take the concentration of protons, right, and you would do this with moles, don't worry about how. You take the log, which is a math thing, you take the negative number of that, and that's your answer, okay? So if we were looking at a substance that we consider neutral, a neutral water solution. Now in acids and bases, something that's neutral is neither. Pure water is not an acid, it's not a base, it's neither. The hydrogen ion concentration of pure water is 10 to the minus 7. All right, what that means is if I could count up the number of hydrogen ions there, whoops. There are that many hydrogen ions in the solution that I'm looking at. That's what 10 to the minus 7 is. Now, down below, I show you the math. That's how you come up with a pH of 7. Look over here. Pure water, in neutral pH, has a pH of 7. Here's the easy way to do it. If someone says that the concentration, I need to write this. If someone says to you that the concentration of protons, the concentration of hydrogen ions is 10 to the minus 10. What's the pH? Don't do the math. Don't pull out your calculators and do that. Just look at the equation. So something with the proton concentration, the pH of 10 to the minus 10, has what pH? I'm going to play the Jeopardy thing. See how easy that is? Yes. See how easy that is? Now, until you need to in the future calculate this, that's how you can figure that out. Now, let's go in reverse. Something that has a pH of 4, pH 4, what is its hydrogen ion concentration? Like, what is that, tomato juice? Well, hold on, Sadie. I'll get something about it you do, so hold on one second. So something has a pH of 4. What's its hydrogen ion concentration? What's its proton concentration? Remember, you can write on the whiteboard. So you can write it just the way I did in scientific notation, if you know what that means. Is that right? 1, 2, 3, 4. You couldn't have done it in scientific notation, Isabel. You're right. I'm sorry. But if we tend to the what? Thank you. Isabel, you are right. I'm not saying that. It's just now I got to count zeros. But yes. Okay? All right. Now Sadie's question, memorize. All right. Memorization is, not the best way to learn something, but sometimes it's the only way. How do you know your phone number? You memorized it, right? So here's what I want you to know about the pH scale. You already understand how to calculate proton concentration or pH, backwards and forwards. That's what I was just showing you. Here's what I'm not concerned that you being able to tell me that tomato juice is an acid, household ammonia is a base. Here's what I want you to know. If the pH is 7, it's neutral. Something with a pH of 7 is neutral. And really the only thing out there that has a pH of 7 is pure water, but actually pure water in a vacuum. So add that for me, please. Is there 2 C's or 1? Oh, God, dumb word. Vacuum. Pure water in a vacuum, and that means no air. If the pH is less than 7, that's an acid. If the pH is greater than 7, that's a base. The further away from 7, the stronger the acid or the base. So household bleach is a stronger base than milk of magnesia. Battery acid is a stronger acid than black coffee. Okay, one more thing I need you to know. Any questions on that? And you can see in the pictures on the left, that's what we're looking at, is proton concentration. Acids have lots of the little things in red, the protons. Neutral or equal, see? Proton concentration equals hydroxide concentration, and base it's the other way around. All right, I got one more slide, and I may run just a minute or so over, folks, so just stick with me. I'll make it quick, I promise. All right, now, one more thing you need to know. How much stronger is the acid or base? Okay, the way that works is if something has a pH of 5, black coffee, and something has a pH of 2, gastric acid, take the difference. All right, now first of all, which one of those is the stronger acid? That with a pH of 2 or that with a pH of 5? Which one is the stronger acid? 2. Okay, now, which one, just so we understand, which one is a stronger base, bleach or milk of magnesia? Right. It's the further, think about 7 as being in the middle. Okay, so back to what I was saying. How much stronger acid is what? Gastric juiced and what did I say? Black coffee? Take the difference, that's 3. Use that 10 and the exponent again that we've been writing. That's what your exponent is. 10 to the third, folks, is 1,000. Okay? Or, here's a simple shorthand. Take the number 3 on your paper, put 1, and add however many zeros. That's how much stronger. So gastric juice is 1,000 times stronger than black coffee. We good? We got one more slide. You guys have been really interactive today. I appreciate that. Okay. Oh, back to buffers. Well, no, I'm sorry, not back to buffers, back to homeostasis. So this last slide is going to take everything we know about the pH scale and it's going to discuss homeostasis. In your body, there are substances called buffers. If your body becomes too acidic, then what these buffers do is they absorb those protons. See, if your body becomes too acidic, that means too many protons are being donated. So this other substance, this buffer, absorbs it. If your body becomes too basic, there's not enough protons. So this buffer substances will start to release them. So it does what I've been showing you in the equations before in response to the pH of your body, therefore maintaining homeostasis. Your body needs to stay about not necessarily 7. Your stomach has a pH of about 2, but it needs to stay the pH it's supposed to be. One of the best examples of buffers is in your blood. It's called chloric acid. Now let me show you the way this works. If your blood becomes too acidic, you got too many of these. Bicarbonate ions, which come about because carbonic acid dissociates in your blood, bicarbonate ions begin to absorb the protons, and even though these arrows are written equivalent, if your blood was too acidic, that bottom arrow saying we're going to the left would be bigger. Okay? Now, if on the other hand, the number of protons decreases, it becomes too basic, then what happens is the top arrow, that equation is dominant. All right, so it's all about that one right there. If this one goes up, the equation goes left. If this one goes down, the equation goes right. Hopefully I didn't confuse you with all that. So protons go up, equation goes left, up, right, and if those go down, the equation goes right. Let me just type that in there. I'm trying to write it in there with my pen. So anyway, it goes up, equation goes left, hydrogen ions go down, equation goes right. And that's a buffer, and that's going to change as your body needs it. Sorry, I did go over 2 minutes. I owe you all 2 minutes. So I'm going to stop the recording right there. Of course, if you have any questions or need to talk to me, I am in office hours by all means. If not, I will see you guys next week. Lab number 2, closed-toed shoes, and a copy of the lab, please.